This is our Rigaku X-ray generator and detector system. So I'll give a brief overview of the major components. The generator itself is located in the center. Below is the control panel, full of the electronics. And up here in the center of the table is what's known as the tube tower. Inside the tube tower is where the X-rays are generated. We'll get back to that in greater detail in a minute. We have two detectors here. One is an older detector that doesn't get used too much anymore. It's an image plate detector on this side of the tower. And on this side, we have our relatively new pixel array detector from, it's a Detector Details 200K. It's very nice. In fact, it's 2 generations better than the image plate detector. There was a CCD device in between that was popular for a few years. Okay, so we have to discuss radiation safety. So the system produces X-rays, which are a form of radiation which can be hazardous in certain situations. We have several safeguards in place to protect users from unnecessary exposure to radiation. The first is that the entire system is enclosed in a large glass and metal box. And the glass is a type of glass that is not X-ray transparent. The second safeguard is that during the experiment there are doors that slide, and those doors need to be shut. Once the doors are shut, I can press this button and this light will turn green. Once that light is turned green, that indicates that the doors are shut and that the user can use the computer to open the shutter to allow the X-rays to come out of the tube tower. Only if the door is shut can you do that. So if I were to open the door during the experiment, you would see the light would come off and the shutter would be closed. That's to prevent accidental exposure. And the third safety device is that all users have to wear the symmetry badge to monitor any accidental exposure. Okay, so an overview of each of the physical components of the generator. Down below here we have the control panel, which allows us to turn it on and off and adjust the settings. Below here are the advanced settings for administrator operators. So the X-rays are generated within this copper box located right here, which is under high vacuum at all times. Inside is a rotating copper anode and a tungsten filament, which 40K volts and 20 milliamp current goes between them. I'll get more into the rotating copper anode in a moment. This red light here indicates that the instrument is on and that X-rays are generating within the tube. These two small lights here are the shutter lights, and those only illuminate when the shutter is open and X-rays are allowed out of the tube tower. In between the tube tower and the mirror is a small beryllium window, which I'll show in detail in a minute. So the X-rays are able to go through the beryllium window when the shutters open into the mirrors here. And the mirrors, they doubly reflect the X-ray beam, and what that allows for is that there is a improvement in the intensity of the wavelength that we want, which is for copper anodes is 1.5418 angstroms. After the mirrors, the X-rays travel down the collimator, which has a series of descending size pinholes in it, finally resulting in the end of the collimator here, where we have a 0.3 millimeter pinhole. At the center of our system is this copper box known as the tube tower. Inside the tube tower is a high vacuum, and also inside is what's known as the rotating copper anode. So this anode is made of copper, and that choice of metal gives us the characteristic wavelength we want. And by rotating, I mean this section here will rotate at high RPM during X-ray generation. So I'm calling this the anode because that's one side of the electron's current. This is a cathode made of tungsten, which is located inside there and sits approximately here. So under high vacuum, a stream of electrons, and in our case, it's set to 40 kilovolts, 20 milliamps. That stream of electrons flows from the cathode to the anode. And as the electrons strike the anode, when they interact with the copper atoms, an electron is displaced from a low orbital in the copper atom. Then when another electron drops down from a higher orbital to a lower orbital, then an X-ray photon is produced. Although this system produces X-rays, it is inefficient, and much of that electric energy is dissipated as heat. That is the reason this needs to rotate. If the electron source continually bombarded the same spot, it would quickly heat up and burn a hole in it. So the anode rotates, and also it's water cooled. So while it's running, there'll be chilled water pumped through the anode, and there's actually tubing that comes out, and the anode itself is filled with water. That's how the X-rays are generated within the tube tower. Now, in order to use the X-rays, we have to let them out of the tube tower. So on each side, deep in here, in between the mirrors and the tube tower itself, is a beryllium window. So basically, a beryllium window is simply a hole drilled in the copper, and then this is screwed into that hole, and that little center part is made of beryllium. Now, beryllium is a metal that has a special characteristic where it is X-ray transparent, yet since it's a metal, it can be used to hold the vacuum. Once the X-rays leave the beryllium window, then they can enter the mirrors and travel down the collimator to the sample. There's one more step that keeps the X-rays in there before we want to use them, is a shutter made of copper, which acts like very similar to a shutter on a DSL camera, and is computer controlled whether it opens or not. Okay, this is the goniometer where the sample is put, and this is where basically all the action happens. So we have the goniometer here, which is adjustable, and also we can rotate it manually, or the computer will rotate it during the experiment. This is the end of the collimator where the X-rays come out. This is the beam stop to stop the direct beam, and this is the cryo stream, which continually emits a stream of 100K nitrogen, which keeps the sample frozen, which does several things. It keeps it from drying out, and also keeps it from slipping, and also reduces the amount of radiation damage from the high intensity X-ray beam. So when we put a sample on, the sample is going to be in one of these small loops that are magnetic base. The magnetic base will fit on here like so. So what we want to do next is make sure that sample is centered in the beam and the cryo stream. So if we look up here at our sample monitor, there's a camera here that points at the sample, and the image is shown on the monitor there. So what we'll do is center the sample on those crosshairs. Now I know that crosshairs are where the center should be because that's calibrated ahead of time. So we can adjust the height, and we can also adjust the position with this tool, or where the sample will be in the loop. And you'll notice the loop is empty. We always want to center So now we'll take one of the grown crystals from an experimental plate and load it onto the X-ray machine. So here we have our microscope that will be able to look at the sample, our crystal plate here, some assorted sample loops of different sizes, and as well as a working stage. I usually use the lid of the tray to work on. So I've taken one of the cover slips off the plate, put it on the microscope, and I'm going to use one of our sample loops to pick up the crystal. So basically these sample loops have a magnetic base that fits onto the goniometer on the machine, and on the tip of the metal shaft is a small nylon loop that allows you to pick up the crystal. I have several because you need a variety of sizes because you want to match the loop size to that of the crystal. Okay, now I have the sample loop mounted on the goniometer with the crystal in it. And if we look at the video display, we can see the loop, the end of the loop, as well as the crystal. The next step will be to center the crystal on the crosshairs. And I know that that is where the beam is because the machine's been calibrated ahead of time. So, using the goniometer, I can adjust the height by spinning this wheel. So we've got the height right. And then if we rotate the goniometer, like so, you can see the crystal move around. And then using the camera angle, I'll use this tool center the crystal. And now we can see it's centered on the crosshair. At that point we can lock the goniometer in place. And now we're ready to do the diffraction experiment. So again we have our X-ray collimator coming out here, our beam stop, our sample centered, and our cryostream keeping the sample cold on the goniometer. At this point we shut the doors. And I can push the shutter button here, and that arms the system so we can control it with the computer. Okay, so now some details about our Detector Pilatus 200K detector and associated AFC11 4-axis goniometer. So the Pilatus 200K is a pixel array detector, and what that means is that there's 200K or 200,000 individual pixels on the face of the detector. Each pixel is capable of counting individual X-ray photons as they strike the detector from the diffraction in the experimental sample. So the actual face of the detector is fairly small. There are much larger ones available, the 2M and the 3M, which have 2 and 3 million pixels respectively. Those are extremely expensive and are normally only seen at government synchrotron sites. However, even though ours is a smaller size, it's perfectly acceptable to use with a little creativity with the associated AFC11 4-axis goniometer. So the 4-axis goniometer means it can rotate the sample in 4 directions. So the first direction that it can rotate is an omega, and I'll move omega now, and that is the axis of rotation, but the crystal gets rotated as you collect your data set. So typically omega will move and will hold the other axes constant. So that's omega. Another direction it can move is the 2 theta angle. Now what 2 theta does is it moves the detector itself, and this allows us to collect higher resolution data at the same detector distance. So now I'm moving 2 theta, and you can see it move. And 2 other axes of rotation are chi and phi. And what those allow you to do is to collect all your HKL reflections. And there's a Rigaku strategy program that determines the best crystal orientation. And by moving chi and phi and holding those steady during the experiment, you can get more efficient collection of all the spots. So I'll move chi, and that moves the small goniometer itself up the ramp there. You can see it go up to about 30 degrees. And then what phi does is it rotates the crystal independently of omega, which is the collection axis. So if you look closely, you can see phi being moved. And of course we can change the detector distance during the collection. Right now it's at 200 millimeters, which is sort of the working distance when you put your crystal up. So I can move that in closer. And here it is moving in for a collection. So again, that's the AFC11 4-axis goniometer. It has 4 axes of rotation plus the movement of the detector, and that allows us to use the pixel array detector as efficiently as possible. And you'll see that later when we set up a strategy to collect. Okay, this is our software. It's called HKL 2000, and this drives the generator detector system and also allows us to look at and process our diffraction data. So, if I look here in the align step, we can see video of our crystal. It's centered. I can turn the goniometer with the computer, confirm that it's centered on the beam. And then if we go to our collect tab, we can set up an initial collection. What most folks do is they set a short exposure time of about 10 seconds at the default distance. And we also do 2 frames with step 90 degrees. That allows us to get a shot of the crystal in one direction, rotate the crystal 90 degrees, and shoot it again in the other direction. This will ensure that if it diffracts well in one direction, we want to make sure that it diffracts well in the other direction. And that'll be a quality crystal. So if I hit collect sets, you'll see the computer's responding up here in the terminal, and that's sending commands over to the goniometer and detector to get it set up in its proper position. Here comes the detector up to the 60 millimeter distance that I told it to. And we can see here that that small red light just came on, and that indicates that the shutter's open. And the software knows that the shutter's open too. So our initial image just popped up here, and this is good diffraction. This was your experiment, and this was your first image, you'd be extremely excited. So a couple things I want to point out. There's a white space in between, in the middle of the detector, and there's a second image at the 90 degrees. So again, that image diffracted very nicely, and this is a very good crystal. So this white space in between the two, in the middle of the vertical part, in this detector, it's actually 2 detector chips, and we can see one detector chip on the top half and one on the second half. And the software knows about that space, and that's just fine. Then this vertical white bar here, that's the shadow of the beam stop, where the direct beam is right here. You can see individual spots of reflections, and then the red rings are different amounts of resolution out to 2.3 angstroms on this, at this setting. So once we have our initial image, we're going to set up the system to collect a full data set. So we're going to minimize this window. We don't need that right now. And we're going to look at the image in the HKL 2000 software. And here's our image. So first thing we need to do is index it. So we'll do an automatic peak search that identifies peaks. It found 378. That's plenty. Go to the indexing tab and we'll do an index. What that does is it measures the distance between the spots, and it knows the distance of the detector and the rest of the geometry, and is able to come up with the space group and the unit cell dimensions. So in this case, we've decided it's primitive tetragonal with these unit cell dimensions here. So these are what it measured, and the second line is what it needs to be to satisfy the requirements of that particular unit cell. Okay. So I'll refine it a couple times. Okay, so there's our, so what we're looking at now is the yellow spots are where the predictions of the spots are based on this unit cell. And they match up with where the spots really are. So, cell is indexed. We know it's a P4 space group class. And we know the dimensions of the unit cell, A, B, C, and the three angles, alpha, beta, gamma, and 90. So now we'll set up to collect a full data set based on the indexing of the initial image. So we're going to use the Rigaku strategy program here. And what this does, basically the concept is, if you index the first frame, you can then predict where all the spots are going to be, regardless of how you move the crystal or the detector or anything. It's just a mathematical prediction. So software is going to allow us to come up with a collection strategy to collect what we want. So it knows the crystal information here, and we'll give it some parameters that we want to get to. Completeness, we want 99%. Resolution, defaults to 2. I'm going to set it to 2.0 because it actually diffracted better than what we could see on the first frame. We give it a redundancy that it wants to get. That's where it measures each spot more than once. The width, that's pretty much fixed. That's how much degrees for each frame. Exposure time, 10 seconds is plenty. And then for detector resistance, it's giving us a suggestion of 37 millimeters. I feel that's awfully close, so I'm going to change that to about 50 millimeters. And then we'll generate a strategy which should be able to collect all the reflections based on that first indexed image. And here's our results. So it's figured it can do it in a single scan, detector distance of 50, and that'll allow us to have a completeness of 98.8, redundancy, and here's some graphs to predict how long it's going to take, how the completeness is going to occur over time, and the resolution of the structure. So from here, we can bring the scans, the calculated scan, back to HKL 3000. We see it listed here. We then set up our data collection, double check that it's right, we set up to collect. So at this point, the detector is moving into position. Okay, so the collection started, so every 10 seconds it's going to refresh and show a new image of that crystal. So this will go and collect 441 frames, 10 seconds each, and that'll end, I'm going to tell you the time it's going to end here. And that'll be a complete data set. And then in the next lecture, we'll take this complete data set and go ahead and solve the structure.